In the 1920s, Clyde Tombaugh grew up in hard times and built telescopes using leftover farm implements. To check the accuracy of his best telescope, he sent drawings of Mars and Jupiter to the Lowell Observatory in Flagstaff, Arizona. They were looking for staff, and he was hired. Along with observing the stars, he stoked the furnace and shoveled snow. But one assignment made history. Day after day, he'd use this machine, known as a blink comparator, to look for anything in his images that moved. It was tedious, painstaking work, but on plates taken on January 23rd and 29th and analyzed in February, he saw a small dot that did move against the fixed stars. Announcing the results after careful confirmation, the observatory made it easy to find the new planet by adding arrows.
This is an incredible work of observational astronomy, and having done something similar but with much more powerful tools, I can really appreciate his achievement.
For decades, Pluto remained, more or less, a point of light. But in the mid-70s, Dale Cruikshank and colleagues attached cameras with infrared filters to a telescope at Kitt Peak.
Detectors or sensors had been improved, and larger telescopes had become available. Well, we did that work in 1976 and found evidence for frozen methane on Pluto's surface. It was several years later that we found the evidence for the other ices.
In 1978, astronomers Jim Christie and Bob Harrington analyzed new plates taken at the U.S. Naval Observatory in Flagstaff. Christie noted an elongation to the north of Pluto. 1 month later, the bump had disappeared. From this and other evidence, they concluded that Pluto, like Earth, had a moon, Charon. From eclipses between Pluto and Charon occurring in the 1980s, astronomers calculated that the moon was almost half the size of its parent body, so large that both objects spin around their mutual center of gravity, outside Pluto. Pluto and Charon were the first double dwarf planet combo discovered in our solar system. Using the basic physics of their orbits and the distance between them, astronomers could calculate their mass and size. Pluto was a little smaller than Earth's moon, about 1,500 miles in diameter, and had only 1/10 its mass. Between 1985 and 1990, astronomers were in luck. As Pluto and Charon orbited their mutual center of gravity, each passed in turn in front of the other. The so-called mutual events allowed astronomers like Mark Bowie to capture the changing patterns of light. Patiently, Bowie created a map of Pluto. Pluto turned out to have one of the two most contrasty surfaces in the entire solar system. In the mid-90s, Bowie and Alan Stern used the Hubble Space Telescope to make the first direct images of Pluto's surface.
And it's exciting to Mark and I and to our whole scientific team to be able to see this object that no humans really could glimpse as a real planet, as a real object in the solar system previously.
In 2005, Hal Weaver and Alan Stern used the Hubble for another close-up look at Pluto and Charon. They discovered two small, dim moons where only Charon had been seen before. Now we know from Mark Showalter's work that there are two more moons, making the current total of 5, and that Pluto is a genuine mini-planetary system. From its size and orbit, astronomers estimated that Pluto is perhaps 70% rock and 30% ice. That makes it one of the largest of a whole new class of objects, the ice dwarf planets, making up what's known as the Kuiper Belt. This region is named for Gerhard Kuiper, a leading mid-20th century planetary astronomer. Kuiper suggested that the solar system didn't end with Neptune and Pluto, but that there should be a disk of other worlds beyond them. In 1992, from a mountaintop in Hawaii, David Jewett and Jane Liu found the first Kuiper Belt object. They were using new and highly sensitive CCDs, like the sensors in a modern digital camera. But their technique was essentially an updated version of Tombaugh's work. Take carefully registered images of a patch of sky and see if anything moves against the distant stars. This one, QB1, did just that. It was only a few hundred kilometers across, 10 times smaller than Pluto, but still huge compared to a comet. Since then, teams of astronomers have found around 2,000 KBOs. Informed by cutting-edge astronomy, But with a fair dose of artistic license, let's take a trip through this third zone of our solar system.
We used to think of the solar system consisting of two different types of planets. The planets we call the terrestrial planets, which are Earth-like planets. That would be Mercury, Venus, Earth, and Mars.
Next out, the asteroid belt, fragments of worlds smashed to pieces by gravitation and collisions. Then come the four gas giants: Jupiter and its moons, Saturn with its magnificent rings, Uranus, also ringed, and Neptune.
And then Pluto was this kind of, odd guy out. It was this little object at the edge of the solar system. And then when we found all these other Kuiper Belt objects, this is kind of almost a third type of object.
So for the first time ever, we'll be able to fly by a brand new object, an object that's been forming for billions of years, and understand what outer parts of the solar system are all about.
By July 2015, we'll know for sure what Pluto and its moons look like, and that will provide breakthrough information on all those other ice dwarf planets, the most numerous planetary objects in the entire solar system that make up the Kuiper Belt. Actually, the Kuiper Belt is more like a donut, bulging up above and down below the ecliptic where most of the planets move.
It's kind of like the asteroid belt, but much bigger. It has hundreds of times more objects in it than the asteroid belt.
Let's now visit 5 named KBOs in the exact positions they'll be in on July 14th, 2015, the day when New Horizons flies by Pluto. Quawa was one of the first Kuiper Belt objects discovered. It's about 1,000 kilometers in diameter, a reddish world, covered in water ice, methane, and ethane. And like many KBOs, it has a tiny moon of its own, Waywa. Up above and down below the plane of the solar system, numerous KBOs have been flung about by Neptune's gravity. This region is known as the scattered disk. One of the largest of these KBOs, Eris, is close in size to Pluto and is made of rock and methane ice. Astronomers categorize KBOs by the tilt of their orbits relative to the plane of the solar system. And one of the more highly inclined orbits belongs to Makemake, named for a Hawaiian creation deity.
Some of these have methane or water ice on their surfaces. Some of them just seem to be covered in some brownish gunk. There are gray objects out there. There are brown objects out there. There seem to be distinct populations.
Some of them seem to be very spherical, and so they probably have warm interiors, and then others are peculiar shapes which suggest they're very cold and strong.
Perhaps the most bizarre and unexpected KBO is Haumea, a KBO shaped like an American football, made of rock and ice. It's white with red splotches and orbited by at least 2 moons. One of the strangest orbits of any KBO belongs to Sedna, discovered in 2003. Its orbit is the most eccentric of any KBO now known, bringing it as close as 76 AU to the Sun, but then carrying it outward to 936 times the Earth-Sun distance. Sedna's strange 11,000-year orbit seems to link it to an even vaster cloud of objects, ready for exploration by future generations. The Oort cloud is an immense icebox of long-period comets, from 10 to 100 times more distant than the Kuiper Belt, surrounding all the known worlds of our solar system.
There's a real record of the early history of the solar system out there in cold storage at the edge of the solar system.
This is what was left over. Pluto is the first member of that group.
But to begin humanity's exploration of the Kuiper Belt, you first have to get to Pluto. And that means getting a mission approved, a spacecraft designed and built, and delivered to the launch pad on time. And none of that was easy. "2015 may be the year of Pluto, but getting there has taken many long years of effort. And for New Horizons, there's a date when things got started: 1989. It was the year when George Herbert Walker Bush became president, and the Berlin Wall fell. Far from Earth, it was also the year when NASA's Voyager spacecraft flew by Neptune and returned the first images of its moon, Triton. Hairstyles of some New Horizons scientists were very different, but for them, May 5th, 1989 was a most important date.
That's the day that I marched into the then Division Director for Planetary Science at NASA headquarters, Jeff Briggs, as a graduate student, and asked him why we aren't studying the mission to Pluto. And he responded, because no one's ever asked me before. That seems like a brilliant idea. Why don't we do that?
Space missions rely on hundreds, if not thousands of people, but sometimes it takes someone with passion and persistence to make things happen. And for New Horizons, that's Alan Stern.
I was interested in this when I was a boy, so I've been somewhere between in the groove and stuck in a rut for 40 years.
There'd been some thought about sending one of the twin Voyager spacecraft past Pluto to complete the exploration of the known solar system. But in the 70s, the scientific establishment wasn't convinced Pluto was all that interesting. Young grad students like Alan, Mark Bowie, and Fran Bagenal thought differently.
Back in, about late 1989 or so, there was a bunch of us who were really keen to go to Pluto.
And the thing that drew me to it the most was the fact that we knew so little. Here's the frontier.
So it was a bit of an opportunity for young people to come in and say, hey, where are we going to go next? What's the next great frontier that we should go explore? And it was clear, out to the Kuiper Belt.
Alan, Fran, Mark, and a small band of enthusiasts became known as the Pluto Underground.
So we realized to make this happen, we had to get together and campaign hard to make the case to go there and explore this little planet with all its moons.
All through the 90s, there were many competing plans for a Pluto mission, like the Pluto Fast Flyby, the Pluto Kuiper Express. A Pluto mission was on, then off, then on, then off.
If the Pluto mission had been a cat, it would have been dead long ago because they only get 9 lives. And we've had significantly more than 9 stoppages and odd twists and turns.
What finally turned the tide was the National Academy's Decadal Survey, a consensus document from leading planetary scientists that ranked a Kuiper Belt Pluto mission highest in priority for medium-class budgets. Finally, after competitive proposals were evaluated, New Horizons, which teamed Alan Stern with the Johns Hopkins Applied Physics Laboratory, APL, and several other institutions across the country, was selected by NASA on November 29, 2001. Now, plans on paper became metal in clean rooms. In 2004, lead scientist Alan Stern described the mission's key science objective.
Well, you know, the key to planetary science is that you really have to go places to get the resolution, to get up close enough to really see what's going on. We want to get up close and personal.
The very best resolution of current telescopes looking at Pluto would give this kind of fuzzy image of a much more familiar world. But here's what New Horizons would see if flying over New York City. Lakes in Central Park, wharves on the Hudson River.
New Horizons is the first really of a whole new breed of spacecraft that is focusing on a very specific task.
For this first mission to Pluto, the questions are basic. What do Pluto and Charon look like? What are they made of? How do their atmospheres behave?
We had to really be disciplined and say, we can't do everything. Let's focus on the primary questions and design the instruments to answer those primary questions.
The long-range imager, LORRI, will be used for navigation approaching Pluto and close-up views during the flyby. The wide-angle camera, Ralph, has both visible light and infrared sensors to map Pluto and Charon and characterize their icy surfaces. There are 2 fields and particles detectors to probe the solar wind at Pluto. The large radio antenna is an essential communications device, but both REX and ALICE, an ultraviolet imaging spectrometer, are part of experiments to analyze Pluto's atmosphere. And there's the Venetia Burney Student Dust Counter, built by undergrads at UC Boulder, and honoring the schoolgirl who named Pluto back in 1930. Together, the 7 science instruments comprise the most powerful set of detectors ever sent on a first flyby of any world in our solar system. But their innovative and highly miniaturized design means that even when all are operating, they draw less power than half a 60-watt bulb, and they're intended to work together seamlessly. After building comes testing, but always with an eye on the clock and the calendar.
It's very, very important that we launch in either 2006 or 2007. We have to make that deadline.
If you want to fly to Pluto on the quickest route, you need Jupiter in position. And that means we have to launch in January of 2006.
It feels a little bit like being strapped to a train going 500 miles an hour.
The test program involves teams of engineers at Johns Hopkins APL and then at NASA's Goddard Space Flight Center.
Once we launch this, we can't go after it with a screwdriver. We can't go fix anything that isn't working.
We make sure that we carry plenty of spare equipment on board the spacecraft. If our main computer breaks, we have a backup. If our main transmitter breaks, we have a backup.
One of the things we do is we put the whole spacecraft on a gigantic vibration table, a paint shaker, and shake it. And then test it after that, and shake it again and test it again. So that's what we're doing from now until launch.
Along with testing the spacecraft, New Horizons needs to train and test its human operators. And for a mission planned to reach Pluto in 2015, it's important to have young people on board early, so they'll be around at close approach.
It's good that we can do that, so they will have both the time, the focus to stay with the mission over this long period of time.
Many of the faces you see around Mission Control in 2004 and 2005 are young and enthusiastic spacecraft engineers.
Normally we're focused on subsystems and instruments in the spacecraft surviving that duration, but